Log on, tune in, find out. Another good idea from Cambridge.
Very great pleasure now to introduce Professor George Ellis, who is Professor Emeritus of Applied Mathematics at the University of Cape Town, South Africa. He has had a wonderful career in relativity and cosmology. I remember from my youth a very difficult book by Hawking and Ellis on the large structure of space-time. My goodness. He's been a university lecturer at Cambridge and Professor of Cosmic Physics at the International School of Advanced Studies in Trieste, and many other professorships. He's been in South Africa now for many years. He's very interested in the science-religion field as a whole. We've got a book by George Ellis and Nancy Murphy on the bookstall on Moral Nature of the Universe. He is one of our Templeton Prize winners, who we're very privileged to have over this few days, and he's also a fellow of the Royal Society. So it's a great pleasure to have you speak to us, George.
Well, thank you very much. It's really nice to be here with you all, and I have been aware for a long time of how Lemaître really was the father of the Big Bang. I think it's really true. Okay, so I'm going to talk about the multiverse science and ultimate causation. So the idea of the multiverse, an ensemble of universes or universe domains, has received increasing attention, and we've heard about that from earlier from Martin Rees, and today we heard it from Don. In separate places, in separate times, the Everett quantum multi-universe, other branches of the wave function, the cosmic landscape of string theory, embodied in the chaotic cosmology, or totally disjoint. These are all being proposed as various versions. And Martins explains the idea, Rees explores the notion that the universe is just past a vast multiverse or ensemble of universes in which most of the other universes are lifeless. What we call the laws of nature would then be no more than local bylaws imposed in the aftermath of our own Big Bang. In this scenario, our cosmic habitat would be a special, possibly unique universe where the prevailing laws of physics allowed life to emerge. And so there's the multiverse, these, in some sense, parallel universes. And of course, the latest public incarnation, Brian Greene's book, The Hidden Reality, Parallel Universes and the Deep Laws of the Cosmos. Now, I have a problem with this title, The Hidden Reality, which we will come back to. So, but he proposes in his book 9 varieties of multiverse in this book. The invisible parts of our own universe that Martin Rees talked, when you go beyond the visual horizon, the universe keeps going. The chaotic inflation, the brain worlds versions, cyclic universes, the landscape of string theory, branches of the quantum wave function, holographic projections, computer simulations, and the idea that all can exist must exist, the grandest of all multiverses. So these are the 9 types which Brian Greene mentioned in his book. Now the first point is they can't all be true because they conflict with each other. So somehow he hasn't quite made a decision which of these he's supporting and which he's saying he doesn't believe in. So maybe none of them is true. Maybe there's just one universe, so that's the 10th option. The big issue is that, in my view, the very nature of the scientific enterprise is at stake in the multiverse debate, because actually what is happening is multiverse proponents are proposing weakening the nature of scientific proof in order to claim that multiverses provide a scientific explanation, and that's what we're going to go into. So I think in order to make their claims, they are proposing weakening what we call science. It's a dangerous state because, and I must emphasize, we're concerned with really existing multiverses, not pathetical or potential or hypothetical. There's not the slightest problem in envisaging hypothetical or potential. It's really existing ones where the problem comes. The central scientific virtues are testability and explanatory power. Now the trouble is, in the cosmological context, they are often in conflict with each other. And there are in fact different streams of cosmology, some of which emphasize explanation and some of which emphasize describing what is out there. The extreme cases multiverse proposals where no direct observational test of the hypothesis are possible. As the supposed other universes cannot be seen by any observations whatever, and the assumed underlying physics is also untested and indeed probably untestable. In this context, one must reevaluate what the core of science is. Can one maintain one has a genuine scientific theory when direct and indirect tests of the theory are impossible? Now, of course, people are claiming there are tests, so that's what we've got to look at. If one claims this, one is altering what one means by science, and one should be very careful before so doing, because there are many other theories waiting at the door wanting to be called science: astrology, intelligent design, and so on. And if you have got some criteria for science which is acceptable in the multiverse case, what I'm going to ask you is, what does that theory say for astrology? What does it say for intelligent design and some of the other theories which are sitting there wanting to be called science? And there are, of course, many other examples. Now, the motivation for multiverses, we've heard it, but I'm just going to very briefly go through it. One claim, it's the inevitable outcome of physical originating processes that generated our own universe. So it's been claimed, and we heard that phrase there, it's an inevitable outcome of chaotic inflationary scenario. That's one claim. Secondly, they're seen perhaps by some as the result of a philosophical stance underlying physics: everything that can happen must happen. And actually, I've got quite a lot of sympathy for that. It's the kind of logical conclusion of the Feynman path integral approach to quantum theory, which actually, I believe this is the best way of justifying where variational principles are true. And I've got a sympathy with it, with that stance. It's been proposed as an explanation for why our universe appears to be fine-tuned for life and consciousness. And this, of course, is what Martin Rees has been talking about. So, this is one of the key motivations. The universe is fine-tuned for life. We've heard about it. John Barrow and Frank Tipler's book, The Anthropic Cosmological Principle, set this out in beautiful detail. Firstly, the universe is fine-tuned as regards the laws of physics. If you mess around with the laws of physics in various ways, no atoms will exist, or no planets will exist, and there is no life. That's point one. It's also fine-tuned as regards the boundary conditions of the universe, because if the universe, for instance, was set up so that the total lifetime of the universe was 100 years, there wouldn't be any life. That just as a simple example. So, a universe with varied local physical properties is one scientific explanation of why the universe is such as to allow life to exist. There's a very large, and the word infinite is very often used, infinite set of universe domains out there. This allows all possibilities to occur. And so somewhere out there things will work out all right, because there's this vast domain and things happen by random there, and most of them are useless universes as far as life is concerned, but somewhere it will get right and life will then inevitably occur. And again, I emphasize it must be an actually existing multiverse. That's essential for any such anthropic argument. And so Martin Rees, for instance, says in his very nice book, Just Six Numbers, the electric force to the gravitational force ratio must be very close to this value. The strength of nuclear binding must be close to that value. The normalized amount of matter in the universe must be close to that. The normalized cosmological constant. The seeds for cosmic structures must be 1 part in 10 to the 5, and the number of spatial dimensions must be 3. Now, it's slightly complicated because this assumes these are independent. Actually, they're not independent. If you're going to do structural formation, there's an interaction between the cosmological constant and the sides of the seeds, but nevertheless, that's a detail in the current context. But so, for instance, you've got to explain why are these 6 numbers all in that small range which allows life to exist. Now, you could claim there are many, many more numbers. In fact, I would claim there are many more, but this is just an example. And the specific application which has particular power is explaining the cosmological constant. We've already heard about that. And Steven Weinberg is the person who pushed this particularly. Of course, he's a real heavyweight in the world of physics. You've got to take him seriously. And Susskind has been pushing it in his book, The Cosmic Landscape, and various papers. And we know, we've already heard, the natural value of the cosmological constant is immensely greater than what we see in the universe, and it would not allow life to exist because it would simply blow all structures apart. Too large a value for lambda results in no structure and hence no life. So, anthropic considerations mean that the value of lambda we observe will be small in fundamental units, and John Barrow's already talked about that, Don's talked about that. So what you can do is you justify an actual value of lambda extremely different from the one that is predicted by physics, different by 120 orders of magnitude. And as I say, I think this is in many ways the one we must take most seriously when you've got Steven Weinberg and Lenny Susskind and Martin Rees all saying this is a really good argument for the multiverse. But it makes clear what the Multiverse project is. What the project is making the extremely improbable appear probable. That's what the Multiverse project is about. Now, the key observational point is that the domains considered are beyond the particle horizon and beyond the visual horizon, and therefore unobservable. So here's space-time, that's the beginning of the universe. This is proper distance against proper time. Time is going up, that's our world line, that's where we are at the moment. That's our past light cone. It refocuses back to the singularity because gravity is attractive. There's another galaxy which set off and it crossed our past light cone there, and we saw it up there. There's a galaxy which spread out, it crossed our past light cone there, we saw it up there. And so this is the space-time diagram of the entire visible region of the universe. That's 10 to the 14th years. And as I said, that's proper distance and proper time. Now, it's a bit difficult understanding causal relations here, so we go to the conformal diagram. This is exactly the same. That and that are the same in different coordinates. We've now changed to co-moving coordinates. So the galaxy world lines are now vertical world lines. Now, we've achieved that by stretching the spatial coordinate. We're now using coordinates which are constant at the position of each galaxy. We also reparameterize time so that the light cones are at 45 degrees. And that means we can see causal relations very, very clearly. So here's our past light cone. Now, of course, physical distances are completely misrepresented. So physical distances are completely misrepresented, but causality is represented completely faithfully. So the start of the universe is there, the decoupling of the microwave background is there. There's our galaxy world line. Now here's another galaxy, it goes up there, it sends off light there, which we receive up there. And the merit of this diagram is it shows you that the furthest thing that you can see is there. The galaxy out there, if it sends light up to us, will be received to us some millions or billions of years in the future. We cannot see it at the present time, no matter what technological innovations you may make, presuming we believe in the limit of the speed of light as a limit for communication. So in fact, the visual horizon is here, and we can see all of the stuff inside there. We cannot see anything outside. And let's say, just for instance, we're going to set up an astronomy project for 25,000 years. We'll collect data and we'll analyze it. We won't move from that point because the scale is 10 to the 14 years. Okay? So the start of the universe is down there. That's the cosmic background decoupling, and everything inside there is visible. All the matter, everything outside is not visible. Now, this diagram is not a very good scale. So this is the observable universe, and that's the start of the universe. And it's absolutely fundamental in cosmology. The stuff outside can't be seen by X-rays, gamma rays, gravitational waves, neutrinos. You cannot see it. It's clear now what the observation causal limitations are, but it's better to do it on a better scale. So that's the bit of the universe we can see. This is the bit we can't see. And what the multiverse people are telling you is we know what's happening here from the data we have inside there. In fact, there's no observational data anywhere out there, but the multiverse people are telling you we know what's happening there because we know what's happening. Now that scale isn't a very good scale. We should actually do it something like that. That's the entire visible universe, and multiverse people are telling us we know what's happening over there. Actually, they're saying much, much more than that. We're saying you can go to 100 Hubble radii, 10 to the 1,000 Hubble radii. You can go on this scale back to Cape Town, and you haven't even started on what they are telling you know. Okay? Because they use the word infinity in what they're talking about, which means you've gone 10 to the 1,000 Hubble radii. From what they're telling you we know, from what we know inside there, you haven't started because infinity, you haven't even begun when you've gone 10 to the 1,000 Hubble radii. And so what you've got is a rather extreme example of hubris. We know what's happening there, and we're going to tell you what's happening over there, on the basis of what we know in there. Okay? Given the situation, what are the arguments and evidence for existence of a multiverse? Now, first is the slippery slope, which we heard from Martin, and now we heard from Don. There are plausibly galaxies beyond the visual horizon where we can't see them. So plausibly, there are many different expanding universe domains where we can't see them. Well, yes, there is stuff beyond the horizon, I agree. But this is an untestable extrapolation in the following sense. It assumes continuity that may or may not be true. Outside where we can see, there might be a Robertson-Walker model. When I started cosmology, everybody knew the universe was Robertson-Walker out there. It kept going forever, and forever there was a Robertson-Walker model. That was what was known when I was a student. Now we're told that when you go out there, there's going to be these other inflationary domains. You're suddenly going to come to a wall and everything will be different. There'll be another wall and everything will be different. So those are two different predictions which you get from this. Now, it could be there's a closed model and you go out there and then you come back to the other side, so maybe it's not so far after all. It's actually possible that we live in an island universe. Maybe there's a lump of expanding universe out there, and then 500 Hubble radii away we come to a vacuum, and the whole thing could be asymptotically flat. You can't prove to me which of those is true because you've got not the slightest bit of data about what is going on there. So you can extrapolate if you want to, but there's not the slightest guarantee that that extrapolation is true. If each step in a chain of evidence is well understood and inevitable, then indirect evidence carries nearly as much weight as direct evidence, but not all the steps in this chain are inevitable. It's not clear the thing is going to keep on going in exactly the same way. I used to use the example here of an ant in the Sahara. And the ant climbs to the top of the sand dune and looks around, and by golly, the entire world is made of sand dunes. Okay? It ain't. If employed, in fact, I claim that this idea, the slippery slope, leads to the old idea of spatial homogeneity forever, because that's what the simple extrapolation tells you. The same thing keeps going on forever, the old cosmological principle. I think this does not lead you to the multiverse of chaotic cosmology with domain walls separating the phases. Well, is the multiverse applied by known physics that leads to chaotic inflation? We've already discussed this briefly earlier. The key physics, now there are various versions. One version is Coleman-DeLucia tunneling, and it's combined with the string theory. This is the Lenny-Susskind version. This physics is extrapolated from known and tested physics to new contexts. The extrapolation is unverified and is probably unverifiable. It may or may not be true. In the version we heard earlier today of chaotic inflation, there were parameter values that led to eternal chaotic inflation. There's a rate of rolling down and there's a rate of expansion, and they're in competition with each other. Some values lead to chaotic inflation, some do not lead to chaotic inflation. We've got not the slightest evidence whether the ratio of those parameters is such as to lead to chaotic inflation or not. The physics is hypothetical rather than tested. It is not true that known physics leads to the multiverse. What is true is known physics leads to hypothetical physics leads to the multiverse, and that's a major extrapolation which may or may not be correct, and that extrapolation is untestable. It may or may not be correct. Nobody has been able to do an experiment to show that Coleman-DeLucia tunneling takes place, much less an experiment to show that the string theory of landscape is actually a correct description of fundamental physics. So it is not an inevitable consequence of known physics. It is an inevitable consequence of some hypothetical physics. This is implied by inflation, which is justified by the CBR and isotropy observations, as we heard so nicely today. So is this evidence for inflation? Well, it's evidence for inflation, but it's not evidence for chaotic inflation necessarily. Chaotic inflation is implied by some forms of inflation, but not others. Inflation is not yet actually a well-defined theory, as we heard today. There's some hundreds of versions of inflation. And in fact, not a single scalar field has yet been physically detected, which one might be worried about if one's pushing inflation. Not all forms of inflation lead to chaotic inflation. And one example is inflation in a small closed universe. It's possible that the universe is spatially closed on a very small scale. There is not an infinity of initial conditions out there. There's a rather small number of initial conditions out there, roughly speaking. That's perfectly compatible with inflation. In that case, chaotic inflation doesn't take place because the thing is spatially closed and it doesn't continue to infinity. Now, one of the strong ones which has been pushed by Weinberg is inflation is implied by probability arguments. And it's an interesting argument. The universe is no more special than need be to create life. This is a bit actually in conflict with what Don was telling us earlier today, but anyhow, this is the argument Weinberg puts. So Weinberg says the observed value of the cosmological is confirmation because it's enough to create life, but it's not too close to the ideal to create life. Now, you may or may not like that as a philosophical argument or probabilistic argument, but my point is the following. It's a statistical argument, it's based on statistics. Any statistical argument only applies if the multiverse exists. It just simply isn't applicable if there's only one universe out there. You can calculate any probabilities you like. It does not apply to the real physical world because there isn't an ensemble of objects to which you can apply your probability argument. You can apply it to your theoretical ensemble, of course you can, but that is not giving you the probabilities in terms of what actually exists. We have only one object we can observe. The universe is unique. We can do many observations of that one object, but it is still only one object, one universe. And you can't do statistical tests if there's only one existent entity. In order for this probability argument to take place, you must have an ensemble to which to apply it. And so when you apply this probability argument, you're already assuming the answer. And then, of course, additionally, as we heard already, we don't know the measure to use, but the result depends critically on the measure. In fact, no value of the cosmological constant can prove a multiverse either exists or does not exist. And that's the elementary logic. If a multiverse implies a particular value of the cosmological constant, it does not imply backwards. Okay? That's just basic logic. If M implies L only probabilistically, it does not follow that not L implies not M. That would be true if that was a strict inequality, but if it's a probabilistic one, it doesn't apply either. It may shorten the odds if there's a valid context in which probability applies. There is no value of lambda that proves a multiverse exists. Now, it may be a confirmation of your theory, it may be it may increase the odds, but it is not a proof. In fact, from my viewpoint, what the Weinberg argument is, it is a genuine consistency test. It's a fairly weak one in my view. Nevertheless, it is a consistency test on multiverse that's indicative but not conclusive. And in fact, a probability argument can't be falsified. Consistency tests must be satisfied, but they're not confirmation unless no other explanation is possible. So L implies M only if it is the only possibility for implying M. So if M implies L, the converse only implies if there is no other conceivable explanation from there through to there. Now, Susskind claims the following: you can disprove multiverse if there are closed spatial sections. If we could determine the closed spatial sections with the curvature is positive, that shows K is plus 1. In Suskind's version of the theory, that's not possible. Suskind's claim is that only negatively curved Robertson-Walker models can emerge in a chaotic inflation multiverse. Now, not everybody agrees on that one. And this is one claim is because Coleman-DeLucia tunneling only gives K as minus 1. That's one claim. That claim is already disputed. There are other papers suggesting tunneling to K as plus 1 is possible. But my point about this mechanism, the Coleman-DeLucia mechanism, it's a very, very specific, very speculative mechanism which hasn't been verified to actually work, and I think such verification is impossible. So, apart from anything else, this is depending on a mechanism which cannot be shown necessarily to be true. The other claim you might say is because the spatial sections are necessarily closed if K is plus 1, if those are all there is, the universe closes up on itself, and therefore multiverse isn't true because the universe closes up on itself. But the point about that is this may not be true. What we see inside the horizon, supposing we could prove K is plus 1 inside the horizon, it wouldn't necessarily guarantee that it continues to be positively curved outside the horizon. We could live in a high density lump embedded in a lower density lump outside. So if you see K as plus 1 in the bit of the universe we can see, it doesn't guarantee that it stays K as plus 1 outside the bit that we can see. We could live in a high density lump embedded in a low density universe. The extrapolation may not be valid. So I don't think either of those are conclusive. Okay, now, the reason many people believe it, it is the only physical explanation for fine-tuning the parameters that leads to our existence. And I think this is the reason Martin Rees believes it, and many others. So Martin is very, very aware of the fine-tuning, and Martin and Bernard's paper on this a long time ago was a beautiful paper on fine-tuning. And in particular the cosmologicon. So you say there isn't any other scientific explanation, therefore the multiverse has to exist. That is a very valid supportive argument, but it ain't proof, because if you say this, you're going back to the situation where you say, I've got a good theory, my theory tells me the result, and so the result has to be true, even though I can't verify observationally or experimentally. This is actually a giant step backwards to the days when we did not feel it was necessary to verify our theories by observation. It's a theoretical explanation. We're being told that we've got a good theoretical explanation, so don't worry about observations. That's the message. Similarly, it results from the theory that everything that can happen happens, as suggested by the Feynman quantum field theory approach. Again, you'll be given a theoretical explanation, not observations. You may or may not like this, but this isn't a proof that the multiverse is true. And the question is, which is more important in cosmology, theory or observations? Do we drop the need for testing because we've got such a good explanation that trumps the need for testing? Well, I don't think we do. I think we're on very, very dangerous ground if we say we've got such a good theory, let's not worry about the fact you can't test it observationally or experimentally. The question is, what are your criteria for a scientific theory? And we've got various ones. Satisfactory structure, internal consistency, simplicity, beauty or elegance. Intrinsic explanatory power, logical tightness, the scope of the theory, how much it unifies. Extrinsic explanatory power, its connectedness to the rest of science, its extendability as a basis for further development. And observational experimental support, the ability to make quantitative predictions can be tested, and confirmation of the extent to which the theory is actually supported by such tests. Now these are perhaps 4 kinds of criteria you might have for a scientific theory. It's particularly the last that characterizes something as science. There are many theories about the nature of things in the world and in the universe. The one which separates science from the others is the last one. All sorts of other explanations in psychology about the way people behave, in economics about the way people behave, all sorts of explanations. Astrology explanations satisfy 1, 2, and 3. It's 4 that separates astrology from the rest. These will conflict with each other and you have to choose. And so the question is, are we going to say we're going to drop our need for call because the rest of it is so satisfactory? Now I'm going to put in 2 caveats. Disproof is possible in one particular case. Chaotic inflation can be disproved if we observe a small universe. That is a universe that we've already seen around. It's conceivable that the universe, in fact, is spatially closed with a scale smaller than the visual horizon. That's what we call a small universe. In that case, it's spatially closed. This is the one and only case in which we can see everything that is in the universe. In fact, we see multiple images because we see a galaxy over there, we get another image from over there, another one from there, and another one down there. Because light, in this case, the universe is spatially closed on such a small scale, light can travel around various times since decoupling, and we can see everything multiple times over. Now that is a possibility, because general relativity does not determine the topology of the universe. You can search for this in various ways, in particular searching for identical circles in the microwave sky, and these searches have been done. And also, it is implied in low anisotropy of the cosmic background radiation at large angular scales, which actually is what is observed. So people have done these searches for simple cases. They haven't observed them yet. The simple cases are ruled out, but not all cases are ruled out. This is a very important test of the nature of cosmology. If we ever saw those identical circles in the microwave sky, it would be evidence that the universe is spatially closed on such a scale that we can see everything already. If it is closed on such a scale, then chaotic inflation is not correct, because we've already seen everything and there's one bubble. So this is a very important test worth doing. However, not seeing them does not prove a multiverse exists. Their non-existence is a necessary but not sufficient condition for multiverses. Now, The second caveat is the following. There is a possibility of proof, one possibility of proof which has been claimed. There are these bubbles in chaotic inflation. It's been suggested if the ratio of these parameters, there's a parameter saying how fast they're moving apart, and there's a parameter saying how fast new ones are coming into existence. With some values of those parameters, the new ones come to existence in such a way that they intersect with each other, and this bubble gets intersected by other ones, and that means there's an intersection there, which will be observable in principle by circles in the cosmic background radiation sky. Symbolically, there would be circles in the sky, the interior of that of which is the image of this other multiverse domain, and things there would be different from things out there and out there. Now, there's been a paper on the web claiming that we have already seen 5 such circles. Okay. Now, I don't think very many people believe that paper. It's a very disputed paper. Nevertheless, this is the one case in which you would get evidence of the multiverse idea being true, but there's 2 problems with this. The first one is you're only going to get a small kind of disruption there if the nature of that other domain in chaotic inflation is very different, is very similar to the one we're in. If that other one was very different, as it often states, supposing the number of dimensions of space were different here than here, there would be a great something rather dramatic happening there. You wouldn't just get a small bubble there, you would get a blinding flash of light or something there. But also, if we were in a case like this, where we've already seen 5, what is happening there? It's telling you the rate of nucleation is very high relative to the rate of expansion. And what you're in danger of happening there is that very soon the entire sky will be covered with these bubbles, and that will be the end of chaotic inflation. It won't be eternal. It will come to an end because all of the space that is available for inflation to take place will have been used up. It will all have turned into hot Big Bang, there won't be any chaotic inflation domain left. So if we were to have seen 5, I believe, now we haven't done the calculation, but I think it's true, this would in fact be a harbinger of the state that chaotic inflation is about to come to an end. Now, the point which I think is very important, in many of these books people talk about infinities. There's an infinity number of galaxies with an infinity number of universes with infinity number of galaxies. This claim of infinities in the multiverse is made, for instance, by Alex Vilenka in his book, Many Worlds in One, the Search for Other Universes. I claim this is highly dubious. As Bill Sturg has emphasized to me, infinity is an unattainable state. It's not a big number. Infinity is a state which cannot be attained. That is the core concept of the nature of infinity. David Hilbert said, the infinite is nowhere to be found in reality, no matter what experiences, observations, and knowledge are appealed to. It's a mathematical idea, not something which can actually physically exist. And supposing it was to exist, which I don't believe, it's completely untestable, because if you could see this infinity of galaxies, which you can't, you couldn't count them, because it would take an infinite amount of time to count them, and there's no way that this claim of infinity is a scientific proposal, because there's not the slightest chance you could ever verify it. Vilenka goes on to postulate the universe is but one of an infinite series, many of whom are populated by other planets. He's well aware of the implications, countless identical civilization is scattered in the infinite expanse of the cosmos. With humankind reduced to absolute cosmic insignificance, our descent from the centre of the world is now complete. This claimed existence of physically infinities is not a scientific statement if science involves testability by either observation or by experiment. And to my mind, this claim in the multiverse context emphasizes how tenuously scientific the multiverse idea is. It's an act of huge hubris. Remember that diagram. You're stating not just that we know from that one little domain what happens 10 to the 500 however, an infinite number. Infinity never comes to an end. And you're claiming that little domain there tells you what happens without end. And I think that's very, very weak argument. Remember the conformed diagram. The implication of all of the above, the multiverse ideas are not provable either by observation or as an implication of well-established physics. It may be true. And I'm not saying it's not true. I'm just saying we can't prove it's true. Continuation beyond the horizon is fine, but it's just the same old universe. When you go beyond the visual horizon on Earth, you don't say, wow, this is a multi-Earth. We've come to somewhere we couldn't see from where we started. It's just the same old Earth, continuing on beyond the horizon. The multiverse idea does have great explanatory power in terms of these criteria. explanation. It's very, very good at explanation. It does provide an empirically based rationalization, fine-tuning, developing from known physical principles. So we must distinguish here between explanation and prediction. Successful scientific theory makes predictions that can be tested. Now, the multiverse theory can't make any unique predictions because it can explain anything at all. That's the whole point of the multiverse. Anything you like happens out there, and there's 10 to the 500 bubbles out there. So therefore, because the multiverse can predict anything, it can't explain anything specific. Any theory that is so flexible is not testable because almost any observation can, in fact, be accommodated. So, Scientific American, parallel universes, not just a staple of science fiction, other universes are a direct implication of cosmological observations. This is a scientifically irresponsible statement. Max has told me he didn't say it, the sub-editor said it. Shoskin concludes, the questions such as why is a constant of nature, one number on another, may well be answered by somewhere in the megaverse the constant equals this number, somewhere else is that number. We live in one tiny pocket where the value of the constant is consistent with our kind of life. That's it, that's all, there's no other answer to the question. The anthropic principle is thus really respectable if intelligent design is just an illusion. Okay, in fact, he confuses particle and event horizon in his book. He claims you can see beyond the horizon through the cosmic, beyond the visual horizon through the cosmic background radiation. That ain't true. The contrasting views on Martin Gardner. One of the most astonishing recent trends in science is that many top physicists and cosmologists now defend the wild notion not only that the universe is as common as black holes, but even more common. Gardner goes straight to the point. The scientists who say this have given no evidence for believing that the possible worlds other than this one, useful though they may be as fictions, have real existence. And Bernard's book puts a nice balanced view. I'm not going to read that to you, but Bernard's book, I think we had a copy there, puts the case pro and con. So my implications from this, I conclude the multiverse proposals are good empirically based philosophical proposals for the nature of what exists. They're good proposals, but are not strictly within the domain of science because they're not testable. I emphasize there's nothing wrong with empirically based philosophical explanation. Indeed, it's of great value provided it's labelled for what it is. I think cosmologists should be very careful not to make methodological proposals that erode the essential nature of science and their enthusiasm to support specific theories as being scientific. If you erode the nature of science, there will very likely be unintended consequences in other areas where the boundaries of science are in dispute. It's dangerous to weaken the grounds of scientific proof in order to include multiverses under the mantle of tested science. If there are many other theories standing in the wings, they would also like to claim that mantle. I think it's a retrograde step towards the claim we can establish the nature of the universe by pure thought, and then don't have to confirm our theories by observational experimental tests, because it abandons the key principle that has led to the extraordinary success of science. In fact, we can't establish definitively either the existence or the nature of expanding universe domains that are out of sight and indeed out of causal contact with us. The claim they exist is a belief rather than an established scientific fact. It's a reasonable faith, a strong expansion of nature, but nevertheless it's a faith. The appropriate statement we can make is not multiverse exists or multiverse have been proved to exist or even multiverses have been proved or can be proved, but that multiverses exist is a useful hypothesis. I just want to finish with some issues. Is there a philosophically preferable version of the multiverse? I like Lee Smolens's one, the idea of a Darwinian evolutionary process in cosmology where bits of a universe collapse to a black hole, they re-expand, they create a new universe with slightly different values of the fundamental constants, and evolution takes place. The universe with most progeny, that is most black holes creating most new universes, win. And so the idea is that there's an evolution by natural selection of the fundamental constants. And the idea is that that would lead to constants of physics likely to produce life. Now there's some gaps in this idea. It's not complete, it's incomplete. Nevertheless, I think it's a really important contribution because it introduces the idea of Darwinian natural selection to cosmology. And Darwinian selection is the way that we can build up information, we can build up complexity. It's the one way where we can generate new information where there wasn't information. And so Smolens's idea is incomplete, it doesn't work properly, but I think it's a really important counterpart, it's a contrast to the idea that all of cosmology is governed only by theoretical physics notions of symmetries, variation principles, and so on. Does the idea of a multiverse preclude the monotheistic idea of a creator God? Is the idea in fact contrary to the idea of a creator? No. Already foreshadowed by Olaf Stapledon in his wonderful book Star Maker. The ideas can exist together. God could have chosen to operate via creation of multiverses. I think Don said much the same thing. The fact that you've got a multiverse does not mean God didn't create the multiverse. Indeed, if one believes in a creator God, that's a much greater God than one who created only one universe. Multi-verse proposals, despite what people believe, says nothing about ultimate causation. Exactly the same issues arise from the multiverse. Did the multiverse come about through pure chance, through probability, through inevitability, through design? If you follow the multiverse logic, the only way you can really handle this is to assume there's an ensemble of multiverses and make it probable, and you then get an infinite regress. You make it probable because that's the only way of avoiding. Inevitability doesn't work, pure chance is unsatisfactory, so we've got probability or design. If you want to say the multiverse is probable, you have to have a multiverse of multiverses. All the same anthropic issues arise as for a single universe. Why this multiverse and not another one? Why a multiverse which allows life? What kind of data is relevant for discussing this is important. And what I want to say here, if you're arguing about ultimate causation in cosmology, in the universe or multiverse case, I do not accept that we should only take into account physical data. Physics and cosmology gives you one set of data about the nature of the universe or the multiverse. It's not the only part. Physics only encompasses part of the causal nexus in the real universe. There is meaning in the universe, no matter what some eminent physicists may say. Meaning undoubtedly exists. The fact we're in the room talking with each other proves that meaning exists in this universe. Okay? There is, in addition, good reason to believe in a moral reality. Absolute standards of good and evil, and I've argued that case in my book with Nancy Murphy. I just want to make one point here, which I think is quite funny. Dawkins and Victor Stenger believe in a moral reality. Now, the reason they do is because they both proclaim in their books religion is evil. And they say so in a way which they believe has got validity irrespective of culture, time and place. When they say it's evil, they are implicitly assuming absolute standards of good and evil, and they don't ask themselves, where did we get our standards of good and evil from? So actually, Dawkins and Stenger both themselves believe in a moral reality, even if they don't realize that they do. How does the universe arise? Can it come from nothing? Or does the existence of the universe... So, how does meaning come into... we know meaning exists. We know morality exists. How do they arise? Can they in fact come from absolutely nothing? Or do they reflect underlying aspects of the nature of the universe? One can claim that because we know meaning exists, this isn't possible unless it in some sense reflects the underlying nature of whatever caused either the multiverse or the universe, whichever happens to be the case. There is a quality of existence in our lives which in some sense reflects what truly exists because it does exist and you can't deny it exists. And that is evidence about the nature of the universe just as much as data from cosmology and particle physics. Is the degree of faith required to believe in a multiverse more or less than that required to believe in a creator God? I think because of the lack of conclusive evidence in both cases, the degree of faith required to believe in either is about the same. Both can be argued on the basis of reasonable extrapolation from known data. Neither is in fact provable. Despite scientific experiences, belief in a multiverse is an exercise in faith. Does a multiverse in fact exist? No idea. You can believe what you like. What you find aesthetic, what gives you the greatest comfort? Take your choice. Does an infinite multiverse exist? I don't believe an infinite multiverse exists. I don't believe an infinite universe exists. Martin Gardner puts it this way, there's not the slightest shred of... I think I've read this to you. No, I've read that to you. What is strange is that people who claim to be strong on the difference between science and faith also defend the multiverse strongly. These people, the same people, who say we must really be clear that science is about truth and not about faith, but those same people defend the multiverse. There's a big contradiction going on there. What's needed to change the situation? Determine a viable set of criteria or procedures for what makes theory scientific. Find what methods can adequately justify unobservable entities. And I'm sorry Bill Sturger isn't here because he's thought about this. There are unobservable entities in science. What is it which enables you in a scientific theory to say something exists even though it's unobservable? And there are ways one can argue about this. People like John Prof will know far more about this than I do. And then you must get your theories and you must apply it to the multiverse case. And then once you've got your theory of what makes a scientific, once you've got your criteria, apply it to the multiverse, apply it also to astrology and intelligent design and see how those come out as well. Okay? Put the enterprise on a solid philosophical basis by setting up criteria and then applying those criteria in a consistent way to all of the things that you claim are science. Apply it to some things you claim are not science and see how it works out. Don, in a sense, started this argument with his Bayesian arguments. But, Don, I have to say, you gave a start of what is needed. And in fact, you were actually, in a sense, giving us a set of criteria, but you didn't complete it because you didn't give us a Bayesian probability for the existence of a multiverse. So you set up the philosophical framework, but you didn't give us the answer. What's the Bayesian probability of the multiverse?
I need the theory.
Exactly. That's the point. You need the theory. The afterword on simulated universes. The book by Brian Greene has got a chapter on simulated multiverses. I'm astounded that serious scientists and philosophers can propose the universe could be a computer simulation. I simply cannot understand this. It's totally impractical from a technical viewpoint, from the viewpoint of actually making a computer which can simulate everything we see around us, let alone the entire... In fact, if you believe in a multiverse, your computer would have to simulate the entire multiverse. It ignores the way the human mind is bodily embedded and not an algorithmic computer process. This computer metaphor's gone mad when you say that the multiverse could be a simulation. This proposal that the universe is a computer simulation raises far more questions than it answers. Where is this computer? How did it come into existence? Who built it? Why doesn't it crash everything? And how could you prove that this computer exists? They don't even ask themselves, these people, what kind of beginnings of a proof could there be that we are in a computer simulation? It's absolute fantasy. Protagonists seem to have confused science fiction with science. Late night pub discussion is not a viable beginning. I really am amazed at these books. And you see the trouble with this, when Brian Greene has got a chapter on this about computer simulation, so you can say to yourself, the guy had a bad day or two, he wrote a chapter which doesn't make sense, but the rest of the book is good. But it's not like that. The trouble is, once you've got that chapter in, it calls into question the kind of argumentation you're using in the rest of the book. So, there we go. There we are trying to look from within this universe to across the horizon to the other part, and that's cosmology, and that's metacosmology.
Okay, Gennaro, make it sort of brief.
Thank you very much. For me, I have the same worry as you. For me, there is really a very big epistemological problem. And I ask myself, I mean, the problem is how is it possible that a so large part of the physics community goes towards theories that, as far as we know, cannot be proved, at least in a foreseen time. Because, I mean, in the next decade, this stuff cannot be proved. And I think we should reflect on a problem. We are probably living in a time in which probably there is a sort of a split in the physics community, a very dangerous one, I think, and we should think very carefully about that, between what could be called applied science, that is science only for doing technology or for doing specific application, and pure speculative science. I think that this fracture, this split is really very, very, very dangerous, because pure applied science, for me, is not able to provide hypotheses, to provide two theoretical breakthroughs, and on the other hand, pure speculative science is unable to lead to fruitful solutions, to solutions that could be their consequences. I don't know.
I'll respond to that.
I agree that the split is dangerous, and I think that, you know, there's a problem of theoreticians kind of looking down on applied physicists, which is the dangerous kind of problem. It's quite deep-seated. I agree with you.
Thank you. Nicholas.
There's a terrific book by Ian McGilchrist called The Master in His Emissary about the distinction between the left and the right brain. And it seems to me that some of these extraordinary tendencies could be understood in these terms, that roughly speaking, the left brain tends to want to see everything reduced as mechanism, and roughly speaking, right brain tends to see meanings and relationships. And McGilchrist's thesis is that over the last several centuries, Western culture has become rather dangerously, that the left brain almost declared war on the right brain. And the idea that we are humans and morally completely insignificant, this sort of computer simulation that there are, you know, tend to be any number of other universes, I agree it's complete lunacy. But from a purely left brain point of view, it makes, I mean, I think there's a good psychological understanding.
Yeah.
Oh, and by the way, cosmology natural selection doesn't work. The evolution is.
Yeah. I wrote a book for a paper for theology and natural science called The Myth of a Rational Life. And one of the extraordinary things is scientists try to put forward this myth that they conduct science on a purely rational basis. It's simply not true. And you can look at that for all sorts of evidence. So you start off in the academic world, the rivalries, all the stuff which happens in the academic world. Why do scientists do science? It's not for rational reasons, it's for emotional reasons. And the whole of life is undergirded by emotionality. And there's nothing wrong with emotion. This view that emotion is bad. Emotion can lead you astray, but without emotion, you're automatons. And so this whole thing of the left and the right brain, there's been this tendency to pretend we're rational, which isn't true.
Thank you. Yes.
George, it's been interesting for me on two accounts to see that really one's got untestability in the sense of the multiverse and untestability in the sense of homogeneity in the Friedman, Robertson, Walker models.
No, that's testable. That is testable now.
Homogeneity?
Yeah.
But what I'm saying is maybe the Tolman model might apply. We might be...
The Tolman model is testable. There's a lot of tests which have been proposed and which are underway. So the Tolman model is good science because it is testable.
No, that's what I... Yes.
Yeah.
Thanks for that. Thanks for that nice talk. I liked the point you made about mentioning Bill Stoder that infinity is a state. It's not a number, like other numbers. One consideration I've got is that the multiverse people and the fine-tuning, they're posing a version of the very well-known question posed by the existentialist philosopher Martin Heidegger, which is basically, why does existence exist? But applying that to the universe. If there is a finite number of multiverses, then if there's a finite number of universes in one multiverse, then does that make the problem of fine-tuning go away? Because it depends how fine-tuned the fine-tuning is. Because what would concern me is, under those circumstances, you might end up with the problem that was well known in antiquity of infinite regress.
Yes. I mean, I think John more or less said you had to have, according to the current string theory version, you had to have 10 to the 300 universes to make it a problem. So,
well, we don't know the number, but maybe at least 10 to the 200.
Is that, just to ask for point of clarification, is that the actual number of universes, or do the same universes get repopulated many times?
No, it was just saying that maybe if it all the constants in physics, maybe we would need of the very crude order of 10 to the 200 different sets of constants.
Sure.
So I'm not. If they occur many times, then that doesn't help. You need at least.
Sure. Yeah.
Thanks, George. I have a pesky question, and the main reason I ask it is to sort of highlight just how unfalsifiable these things are. When you talk about possible evidence for a multiverse, and the nucleating bubbles might show up in the CMB.
Yeah.
You suggested that one could, in principle, falsify it by doing a calculation which showed that they nucleate too rapidly, and so
that wouldn't, if it wouldn't falsify it would falsify the idea that it would falsify the idea that that specific chaotic multiverse would last forever, because what it would say is the nucleation rate is so high that in fact these models start off with a compact spatial section. The nucleation takes place in that compact spatial section. Once they intersect each other, you've lost that bit of the inflating part. You rely on the bits of inflation between the ones which are nucleated to continue giving you a chaotic inflation. If the nucleation rate is high enough, you lose all of the inflating thing. It comes to an end.
But in the streamscape, you can always just say that's the end of a branch. You pulled from some deciduous bed.
But if you have a process of new nucleation and new universes, then you have to throw that parameter in well, and there's 3 parameters you have to balance. It gets very, very complicated. And then you could have a situation where the new nucleation takes place and the thing does become a fail. And you then end up with this thing. So there are some parameter values where this will be true. There's somewhere it won't, and you've got not the slightest evidence that the thing lives in that part of parameter space where it will be true and it will remain eternal.
Yes.
I mean, I enjoyed your talk and I almost agree with what you said, but you seem to be making a very clear distinction between what is science and what is not science, so this problem of the demarcation principle.
The problem?
The problem of demarcation between science and non-science, which is a problem of 400 years.
Yeah.
Philosophers of science and lately sociology of science, I think there's no demarcation. Anything that a bunch of people who call themselves scientists are doing that can be thought to be science, like Steve Fuller would argue for intelligent design, for instance.
Yeah.
And I was wondering if it is not science, what is it? Because much of theoretical physics and much of mathematics is, from your point of view, not science, but I would say it's astrology or poetry.
I think rather like the distinction between cosmology and metacosmology, I think present-day theoretical physics is missing a category. Speculative physics is too tendentious a word. Hypothetical physics, proposed physics or something. But if you read current version of Physical Review D, the proportion of papers which relate to even potential testing is not very large. And the nature of physics has changed, what's called physics has changed, so that a lot of it is an investigation of mathematical structures with absolutely no proof that those mathematical structures actually relate to the real physical world in any sense. And whether the word theoretical physics, perhaps the word mathematical physics is a better phrase. One should perhaps separate out theoretical physics from mathematical physics. So I think the shift hasn't only taken place in cosmology, it's taken place actually in theoretical physics. And in a sense, I think the theoretical physicists have brought this way of thinking into cosmology. I'm not claiming at all that there's any simple answer to this question, what is the nature of science? But one does at least have to be aware that there are these tensions between them which are playing out in this case, and that one is making decisions here which are portentous decisions in terms of what science is.
Thank you. Just about one time.
I have a question about claims being made about that, and as far as I can tell, you didn't address these kind of multiverses that certain versions of string theory, or brain theory in particular, entail a multiverse.
The string theory itself does not entail a multiverse. It entails the possibility of a multiverse. To realize that you have to have chaotic inflation as a context within which the string theory potential multiverse can be realized in actuality. So string theory itself is just a potential multiverse. To realize that you need chaotic inflation.
Well, see, when I talked to, this was Gerald Cleaver about this, who's a string theorist, and he said, well, you can, when you have these colliding brains, they generate new brains as they collide with each other in certain versions of brain theory, so that it's not really relying on the chaotic inflation.
Well,
And the brain would be one brain would be an entire universe.
yeah, there's a whole series of problems with this. Firstly, we have no evidence that a single brain exists. Secondly, we have no proper theory of what happens when brains collide with each other. When he says that when brains collide this happens, he's giving you a speculation which might be a direct speculation. It's actually, as far as I'm aware, not in a sound mathematical footing, let alone having been proven to relate to any actual physical thing which actually exists somewhere out there.
Thank you. I think we have to draw it to a close. That's a brilliant talk. Thank you very much.